Hello and welcome to another episode of How to Understand X. Today we're going to be tackling limits. Um, this is going to be a long video. I suppose that's par for the course at this point. But honestly, I don't know. I think this might be a long video because I just have a tendency to talk far more than I need to. But I'm not really going to be talking about too much today. I'm going to be talking about the delta epsilon definition of the limit, um, maybe some indeterminate forms, L'Hopital's rule for sure, um, how to find like a normal limit, and like continuity. So definitely a good amount of content, but not too much by any means. And I'm actually going to break a personal rule of mine and start with the more complicated part of what we're going to start with, which is the delta epsilon definition of the limit. And we're going to start with the more complicated part, which is the actual definition, and we're going to simplify it from there. So, given the limit as x approaches c of f of x equals L. That's what we're given. And I also feel like I need to say that this is a proof, or not really a proof, but this is a definition and then kind of like an exploration of what that means. So this isn't like what the actual, like how to find a limit. This is what the actual limit means. And this says that for every epsilon, I'm going to write it as a backwards 3, that's greater than 0, there exists, I would use, the math way of writing like that. That means there exists. But, I just want to make sure that you guys can fully understand what I'm saying. There exists a delta greater than 0 such that for every x, the I'm not gonna make it too complicated. Let's just say that the 0 less than the absolute, I should actually write that on a different line. 0 is less than the absolute value of x minus c is less than delta. That also implies that the absolute value of f of x minus L is less than epsilon. So, yeah, this seems pretty abstract, pretty almost nonsensical, but I would encourage you to write that down, or at the very least think about it. And I'm going to erase that, and we're going to talk about it. So, here we go. What did any of that mean? Well, to start, we'd have to break down our two expressions. I suppose you could say that epsilon is greater than 0 and delta is greater than 0 count as expressions, but I'm going to talk about the more interesting ones. We have 0. 0 is less than the absolute value of x minus c, which is less than delta. Yes, it is less than delta. And the absolute value of f of x minus L is less than epsilon. So, what does that mean? Well, we have x here and delta here, and we have f of x here and epsilon here. If we have a, x and y axes, and we define that y is equal to f of x, that only goes to show that, I suppose, the limit as x approaches c, f of x is equal to L is also an expression. But, if y equals f of x, then epsilon is going to be a y value. And delta is going to be an x value because it's dealing with our x right there. And, these are arbitrary values, but since we have for all x, or for all epsilon and for all deltas, this has to be a very broad concept that we're trying to illustrate. So now that we have our ideas that, delta is an x value and epsilon is a y value, the absolute value signs for both of these indicate that this is some type of range. That means that this x, well, I'll start with the f of x minus L is less than epsilon because I think that might be a little bit easier to illustrate. We know that epsilon and negative epsilon are like values that f of x minus L is bounded between. So this is a range. And if we ignore the zeros less than for just a second, and we know that this is a small domain where we have negative delta and delta with x minus c in between. That's what this absolute value is doing to both of these. This is going to be a range between negative epsilon and positive epsilon. This will be a range between negative delta and delta. And again, thinking about our zeros less than, if 0 is less than the absolute value of x minus c, that just means that x minus c cannot equal 0. Like there has to. So, and if x minus c is not equal to 0, then obviously x cannot equal c. But this is just saying that if 0 is less than the absolute value of x minus c, then if x minus c had some negative value, then obviously x and c are different numbers, but still the absolute value of that would be greater than 0. So this 0 is less than the absolute value of x minus c. That part of this expression simply says that x cannot equal c. So we know that this is a range. Both of these are ranges of x and y values. But again, what exactly does that mean? Well, good question. I'm going to very poorly draw two straight lines, which is our x and y axes. I'm going to keep it on the first quadrant. So we're going to have, let's say, this little, that's a function, sure. And we're going to say that this x value right there is c, and actually I should make this function simpler. I'll just draw it again. We're going to do that, and that. We're going to make it a lot simpler. We're just going to do that. And we're going to say that this, that x value is c. So, right there, that'll be c. And we're going to say that that point is, or that y value for that point would be L, because we're saying that the limit as x approaches c of f of x is equal to L. And now, let's think back to what we were saying. We know that x cannot equal c, and for our range here, so there has to be some type of value. There will be a negative delta and a positive delta, so we're gonna write those, and we know that there will be a positive epsilon and I drew and like it's a different symbol that means something else. We have a positive epsilon and a negative epsilon, and these are ranges of y values and x values. that both C and L can fit into. So, with that, let's think about what's happening here. We know that delta and epsilon are arbitrary values. That's sure. We know that. But we have to find like, some way to explain what is happening here where this implies that, where this relationship implies that relationship. This might get into, like, the concept of if then, which is a much it's not easy, I would say, to like comprehend, but it's a different field of math than what we're doing right now. So I don't want to get too abstract with it, but what we're essentially saying is that when we have this range, of negative delta to delta, we are also saying that with this negative delta to delta, we have a range between these y values, where there is a negative epsilon and epsilon. And in between negative epsilon and epsilon, this relationship between f of x and L exists. So, this means that as this, let me try and make this slightly less cluttered. I'm just going to draw the range. We have our negative delta and our positive delta, and we have C. We know that this is a small subdomain that necessitates the formation of a small range between, I really don't know why I'm putting that symbol, between epsilon and negative epsilon, with L, a random y value in between. The formation of this domain means that there has to be a range of those values. That's what implies means in this context. And, if you do, like, I think discrete mathematics is what this deals with. But if you do start learning about if-then relationships, I feel like this might be a little bit more sensible, but I just want you to understand the formal definition before we, like, make it make sense. We know that if this domain means that there has to be a range of these values, the further we restrict this domain, if we have our negative delta and our positive delta all the way out here, we know that this delta in our original expression, 0 is less than the absolute value of x minus c, which is less than delta. We know that delta can be literally anything. I think it was I said either for every delta or for every epsilon, but I mean, not for every epsilon. I said for any or for every, but still, that means the same thing. Delta can be literally any value. We know that there has to be this relationship that implies another relationship, the formation of a range. But if we constrict this delta, if we make this delta smaller, then instead of having such a big spread between negative delta and delta, we would have a much smaller spread. I'm going to put it like that, and then we have that. That will be C in between. And we know if this is our relationship, if we know that delta, this range, or this domain of negative delta, should I use parentheses? I'll use parentheses. This range of negative delta and delta creates, I keep saying range. This domain of negative delta and delta implies the relationship of a f of x minus L is less than epsilon, or the absolute value of that is less than epsilon. And that implies the formation of the range negative epsilon to epsilon. This results in that. And since these two have an if-then relationship, we know that if we constrict our negative delta to delta, then we would have a smaller negative epsilon to epsilon. I think you can kind of think of it as if this box right there is the intersection between this range and this domain, then if we shorten this domain, then this range will then subsequently get smaller. That's perhaps one way to think of it. But essentially, when we constrict our negative delta to delta, or we find a smaller value of delta, then the value of epsilon is also going to get smaller. That was all super abstract, and if some of it went over your head, not only was that a very poor explanation of what was happening without getting too deep into like the woodworks, it's also it's not super relevant to what you need to use limits for, but I hope that what carries across is that the smaller delta becomes, our domain surrounding C, our x value C, the smaller epsilon becomes. That's the that's the range of values that surround L. And so, if you get those two things, that the smaller delta becomes, the smaller epsilon becomes, then you might actually think of this in terms of precision. This might be a little bit easier to understand for maybe some like engineering students out there. I'll rewrite this because I've scribbled over it far too much. We have 0 is less than the absolute value of x minus c, which is less than delta. And then we have the absolute value, f of x minus L is less than epsilon. We can think of this as precision. We want this value to be smaller than epsilon, and we want this value to be smaller than delta. We know that 0 is less than this just means that x cannot equal c. So it's not super relevant to what we're trying to say. But the smaller this is, the closer these two values are going to be. Like, I suppose maybe, let's say that delta, we're going to only work with the left equation right now. Let's say that delta is like 1. And we need to say that the absolute value of x minus c is less than 1. And it can't equal 0. Like x can't equal c, but still. We could say that maybe, I don't know, x could equal 2, and then c could equal 1.5. And if we have our set value c equals 1.5, 2 is pretty close. There's only 0.5 units of distance between x and c. So it's a little, it's pretty precise right now. But if we were to decrease delta even further, we would say, let's say 0.1. We still have our c's equal to 1.5, but what value minus 1.5, well, what absolute value minus 1.5 would equal 0.1 or be less than 0.1? We can't use 1.6 because that would be, exactly 0.1. So let's say 1.55, that's our arbitrary x value, minus 1.5 is less than 0.1. And that's true. You would have 0.05 or 1/20th is less than 0.1 or 1/10. And that's a true relationship. And we know this 0.1 is much more precise than 1. We already restricted ourselves. We made it from 2 to 1.55, which is much, much closer to c. And if we keep on going to numbers that we can't even imagine, we can say that for any delta, some infinitesimally small number, like 0.000000001, there will be some x, like, I'll change our c to like a whole number to make that more easy. It'll be like 1.00000, and I'll just do an ellipses, very odd looking ellipses. There we go, that's an ellipses. And eventually we'll get to 1 is less than some arbitrary delta. And that's what we're trying to say. We're saying that as delta gets smaller and smaller, this implied relationship between this expression, the expression of some domain from negative delta to delta, implies this relationship of a range between epsilon, negative epsilon to epsilon. We're saying that as delta gets smaller and smaller, epsilon gets smaller and smaller. And we know that as delta gets smaller and smaller, this x minus c gets smaller and smaller as well, and therefore x is getting closer to c, or in more mathematical terms, x is approaching c. So we understand what's happening for our first expression. For 0 is less than the absolute value of x minus c, which is less than delta, we are saying x cannot equal c. That is our first idea because of this half, right? X cannot equal c. And then we are also saying that x is getting closer to c as this degree of precision, this delta, gets smaller and smaller, or goes or approaches 0, right? That's basically what we're saying. And then we know that this relationship, well, we don't know it because I feel like that might get a little bit too abstract for, a somewhat simple definition. We at least assume for now that this relationship implies this relationship, which means that as x approaches c, f of x approaches L, or it becomes L. As our degree of precision, our delta gets smaller, our epsilon gets smaller, and therefore the distance between f of x and L closes. It gets closer and closer to one another. And that means that our y value for the point C, or point x equals C, is eventually going to be L. Or not going to be L, but it just trends towards L. So, all of that is to say that the expression, the limit as x approaches C of f of x is equal to L. All this is saying, as x goes towards C, as the expression x minus C gets smaller and smaller, or the absolute value of that expression gets smaller and smaller, then x is getting closer and closer to C. And then f of x, I have no idea what just happened there. 1 second. I apologize for the technical difficulties. I still have no idea what just happened. But I actually kind of lost my train of thought. I forgot what I was saying. But we know that the absolute value of x minus c, if delta is some very, very small value, we know that x minus c, if the absolute value of that expression is getting smaller and smaller, that means that x is approaching or going closer to c. And since this expression implies this expression, that means that epsilon is also getting smaller because delta is getting smaller. And if epsilon is getting smaller, then that also means that the absolute value of f of x minus L is getting smaller. Which means that it's basically the same idea as this one. That means that f of x is getting closer and closer to L. Or, again, trying to simplify this a little bit further, we know that y equals f of x. We defined that already. This expression, the limit as x approaches c of f of x equals L, that expression means that as x approaches some value c, y approaches some value L. For the point x y, this expression means that the graph is trending towards the point CL. So I'm gonna try drawing this out because I really hope that you guys are understanding most of what's happening here. Maybe not all the epsilon and delta stuff, but the approaching stuff, that's really important for the rest of this. But given some graph like that, we'll go back to our curve. We have that, and we have C, and we have L. Our subinterval of like negative delta to delta and negative epsilon to epsilon, as that subinterval gets smaller and smaller, the x values around C, both from the left and from the right, that's important, both from the left and from the right, are getting closer and closer to C. Actually, I'll keep the arrows just to say that x from both sides, left and right, from negative delta to positive delta, are getting closer and closer to C. And similarly, y, the y values, are getting closer and closer to L from negative epsilon and epsilon. Epsilon, negative epsilon being just random arbitrary values. And as delta gets smaller, epsilon gets smaller, and therefore x from both sides, remember, gets closer to C, and y from both sides as well gets closer to L. So, let me draw that graph again. It's getting a little bit cluttered. We'd have this axes, we'd have this, y equals f of x, C, L. We would say that that point C, L, the limit as x approaches C of f of x is equal to L. I hope most of what happened made sense. As x approaches to the value right there, y approaches to the value there. Goes that, both from the left and from the right, it approaches their respective values. So, maybe marinate on that a little bit. We'll do some exercises. We're gonna start with x squared. That's a pretty recognizable function. We'll say the limit as x approaches 3 of f of x is equal to blank, and f of x is equal to x squared. I mean, you could, put x squared in there instead of f of x, but just for our purposes, we're going to keep the f of x notation, because that's what we've been working with so far. So we'll have our x squared right there, right? And our c, which is in this case 3, has to be approaching some y value there. Well, let's think about our points. We have x, y. We have 0, 0. Actually, I'll maybe do some negative values. We'll have negative 2 is 4, because negative 2 whole squared is 4. Negative 1 whole squared is 1. 0 squared is 0. Continue here. 1 squared is 1. 2 squared is 4. And then 3 squared is 9. So, for the point 3y, well, I put my point far higher than y. So even though this graph is not technically accurate, we know that 3y has y equals 9. So if we think back, we have in our, weird definition explanation thing that I did a little over a couple minutes ago now, we have x approaches c. We have defined our c as 3, and the L right there is the y value 9. Now, what does that mean? Well, it means that we could, for many, many limits, try and substitute our c value directly into x. We can do the operation f of c to find L for many, many functions. And I'll define to you the, I suppose you could say, the limits of those functions, or like the properties of those functions that we're allowed to do this operation to. But we can substitute c4x into, I wouldn't say most functions, because there's an infinite number of functions that you can possibly make, but you can say that for quite a few functions you can directly substitute. Remember that term, direct substitution. You can directly substitute c for x to find a good approximation of L. And if we go back to our graph, the one that we have right here, I don't know why I drew a line, I meant to do an arrow, but for that graph that we have right there, we know that as x approaches 3 from the left, we are getting, I'll actually do 4, 16, just to make a point later on. But we know that from the left, it goes 1, 4, 9. It is generally trending upwards. And from the left goes 16, 9, generally trending downward. So it goes like that and that. The y values are increasing from the left and decreasing from the right. That it is the y value, or the function f of x, is approaching 9. That's what the output of this function f of x is trying to get to. So for x squared, the limit as x approaches 3 of x squared is going to be 9. What did that example teach us, or what I hope it taught you, is you can directly substitute for many, many functions the c value into x to find a good approximation of the y value that f of x is approaching as x approaches some random value. And that just comes back down to y equals f of x, right? And if y is a function of x, which is what that's saying, then as x approaches some value, y, I'll keep our c notation. Don't want to do question marks now. But as x approaches c, y approaches L. That's because, y is a function of x. As x changes, y will inevitably change as well. And so, since we have this relationship that y is a function of x, we can, in many, many cases, substitute 3, or not 3, but c for x, and use f of c to find a pretty good idea of what L might be. And that can go super complicated if you want. You can make this into, say, the limit as x approaches 4 of f of x of I don't know, x plus 7 to the third power divided by 19x squared plus 12. Something crazy. And you could substitute 4. I have no clue what this function would look like, so I'm not even going to pretend to draw it. But you can substitute 4 in there, and you'd have a pretty good idea of what that would be. 4 plus 7. I already made this too complicated for me to calculate offhand, but 4 plus 7 cubed over 19 times 4 squared plus 12. If you evaluate all that, you would have a pretty good idea of the y value that, I'll say this is L again, y is approaching L as x is approaching 4. Because, again, y is a function of x and will therefore change as x changes. But still, direct substitution for most functions is a pretty good way to see where the y values are trending towards. And yeah, that's basically what direct substitution means. If you have no clue what to do with a limit, I shouldn't say the first thing, but one of the things you should think about is direct substitution, because that's also a pretty good approximation of what's happening. And so now let's try and throw a dent into our assumption. We know that direct substitution for limits like this is a legitimate strategy. Hold on. We know that direct substitution is a legitimate strategy. What's something that we can substitute? Well, some concept that we can try to substitute but doesn't actually work. I'm of course talking about infinity. We'll look back at our f of x is equal to x squared, and we can say that our c value is approaching infinity. And this is kind of tricky to think about because infinity, well, I can't just say infinity is not a number because there's uncountable infinities, countable infinities, infinite sets, etc., etc. It just gets more and more cluttered. I think I might put some like black pen, red pen video about how trying to generalize infinity doesn't work. Like you can reorganize an infinite set in such a way that maybe like a third of all numbers are even instead of every other number being even, just based on how you organize stuff. So just like infinity's weird, it's not really a number, but we can say as a concept the limit as x approaches infinity of f of x in this situation, if we tried direct substitution, we would have infinity squared, which is infinity because, you know, infinity's weird. But a better way to think of this is to think of the actual graph of x squared. And I'm actually going to say c, if c is approaching infinity, both plus or minus infinity, and minus infinity is just the set of negative numbers. It's like negative 8, negative 7, negative 6. I should have put an ellipses somewhere over there, but still. Negative infinity is also just the set of natural integers, but with negatives. And if c is approaching plus or minus infinity, then I can't say that the limit is going to be approaching plus or minus infinity, because it can actually approach quite a few things. But as c approaches plus or minus infinity, we say that the limit of that is called end behavior, which is a fancy word for saying if there were some type of end to this function, it would either be really big or really small, or not really small, but it would be very heavy into the negative area, or it would be exactly one number. So yes, we see the general trend of this x squared, and we know that x squared is a pretty simple function. You know, it's not going to do anything crazy to us. We know that it's just going to look like that forever on the left and right side. So we can say that the limit as x approaches infinity, which again I feel like I need to reiterate, infinity is not a number, it's a concept, but still, the limit as x approaches infinity is going to be infinity. And I suppose you can say, like, oh, direct substitution, infinity into f of x, you get infinity squared, but I think perhaps a more mathematically, like, sound way of looking at it is seeing that, hey, as x increases in the positive direction, y is also increasing I'll put it as a straight line to make sure that it's easily visible. We know that y is also increasing in the positive direction, which means that if x is increasing in the positive direction, then y is increasing positively. And if there were some magical, really, really big end, some countable infinity at the very end, then there will also be a infinity that y is approaching. But yes, I will put some type of video describing why trying to generalize infinity into anything doesn't work, and videos about how dividing by infinity doesn't do anything. But yes, the I don't know why that keeps happening, but the limit as x approaches plus or minus infinity of some f of x is not equal, but this is called end behavior. And another pretty important concept is we can't divide by infinity, we can't divide by 0, but there are functions that would have infinity in the denominator, would have 0 in the denominator. And I think perhaps the most common one that you might see is f of x is equal to 1 over x. Now, perhaps you might have already seen this function. It looks kind of out there. Let me actually draw that graph slightly better. The graph of 1 over x looks kind of like that. There are asymptotes, or imaginary lines that values approach, and these are the axes. As x approaches 0 from the left, like this might get close to the y-axis, but it will never intersect the y-axis. And that's important, but we'll just say, hey, this is the graph of that function. And now, what do we do here? I'll talk about continuity in just a little bit, but if we were to think about end behavior, I mean, we'll talk about what the, well, I'll spoil it. There's not going to be a limit at x equals 0, but we'll talk about continuity in just a little bit. The end behavior of this function is interesting. Let's try direct substitution. Well, not direct substitution, but we'll think about it in terms of direct substitution. We have the limit as x approaches, we'll keep it positive, as x approaches infinity of 1 over x. I've been using f of x all this time, we might as well keep that notation. F of x, well, what is this? We could say 1 over infinity, but that means nothing. You can't divide by infinity, you can't divide by 0. It's just, it doesn't work. I will try and find some videos that prove why, like, dividing by infinity is just not possible, but we can think about 1 over infinity as a concept, as infinity itself is just a concept. So if 1 over infinity is a concept, we can say that as x approaches infinity, 1 over x is approaching a very specific value. And I know that this graph doesn't really show what that value is approaching very well, but as x becomes greater and greater, the y value, or this 1 over x, is becoming smaller and smaller. And you can use common sense for that. You can say 1/2 is greater than 1/3, which is greater than 1/4, and then on and on and on. And then, it just, reason says that eventually you would get to 1 over infinity, which will be the smallest number. And presumably, if 1 over infinity was an actual number, it would be I'm not well versed in infinity by any means, but I wouldn't say it's greater than 0 or even equal to 0. It's just it is getting very, very close to 0. Using just common sense, we know that um, as the denominator of some function becomes greater and greater and the numerator stays the same, then that fraction is going to become smaller and smaller itself. So the end behavior of such a function would be the limit as x approaches infinity of f of x. In this case would be, oh god, that scared me. It would be 0. And while that doesn't seem too important, I mean, it's a cool example or whatever, this is actually one of the biggest things that you need to understand. 1 over infinity, while 1 over infinity is not a number, within the term of, within like the context of limits, we can say that as x approaches infinity, y is approaching 1 over infinity. And since infinity is a concept and 1 over infinity is a concept, this is kind of a bit abstract, but we're saying that x is getting bigger, and we're saying that y is becoming smaller, but not negative. Yeah, it's a little bit cramped, but still. 1 over infinity means that y is getting closer and closer to 0. And so the limit as x approaches infinity of 1 over x is going to be 0. Or for our purposes of different calculations, we would say that 1 over infinity, the limit of some 1 over infinity, that's going to be 0. And not the limit of x approaches infinity of 1 over infinity. I might actually show a little, not really a proof, but just a nice idea of what happens if you find the limit of a constant, like 4, but still, yeah, the limit as x approaches infinity of 1 over x, that's just going to be 0. And when you see that, because you almost definitely will see that, that's what it means. You are getting closer and closer to 0. And now we're going to talk about limit properties, since I already have the limit of a constant function. We might as well do that. This isn't going to be a proof, it's just a way of looking at it. We can say that, that's 4 right there, that y value. And as x approaches 3, which is right there, we can say that both from the left and from the right, which is pretty important. We can say that both from the left and from the right, the y value is going to be approaching 4. So if there's no input in our function, well, maybe not no input, but if the input does not affect the function f of x, then it's just going to be 4. Or it's just going to be the constant itself. But yeah, that's not really a proof. That's just kind of using common sense. But let's see. I mean, I obviously don't have a script, but I don't know if I should talk about limit properties first or about okay, let's talk about limit properties first. Yeah. So limit operations work pretty similar to our normal operations. So we're going to start, so limit properties, in most contexts, you're just going to be given the limit laws, and that will most likely be enough. They're pretty self-explanatory. I want to be a little extra, so we're going to do a proof for this, even though it's not necessary. I don't know if I should say that, but what we hope to prove is that the limit as x approaches c of some f of x plus g of x is equal to the limit of x approaching c of f of x plus the limit of x approaching c of g of x. And you could be like, oh, that's just, common sense. You can break it up. But the limit is an operation, and I would just like to prove it. I think that it might not help you with understanding because we're going to go back to our delta epsilon definition, which already I feel was perhaps a little bit too abstract, but still. I think it's fun-ish. So let's just say that this, the limit as x approaches c of f of x, we can call that limit 1, and then we can say that this is limit 2. Okay? And so, let me erase these. I hope you understand what limit 1 and limit 2 means. It's kind of self-explanatory. But, yes, we will write down limit 1 plus limit 2. This is called the sum rule. And this is going to be a proof. I'm not trying to show you how to use the sum rule. I'm just saying if we acknowledge this as true, we're going to have to find some reasons why this is true. So we're going to go back to our delta epsilon definition. We have our expression, the 0 is less than the absolute value of x minus c, which is less than delta. Almost put epsilon. Yes. And instead of having f of x, we were going to have the absolute value of f of x plus g of x. I think we should put parentheses just to show that this is our quote-unquote f of x from our original definition. And then this is going to be minus the L, remember? So it would be in parentheses L1 plus L2. Because if this was some function like h of x, and then this was L, that would just be our normal limit concept. So, yeah. Nope, I do not want to do that. We're just gonna, we understand that so far. L1 plus L2, and that is going to be less than some arbitrary epsilon. So, yeah, maybe write that down. And let me erase this. We're going to actually, well, we know that the relationship between those two, I'm not going to write them out because this is going to last forever, but we know that the first expression implies the second expression. So we can just kind of think about it a little bit in reverse. We can say that for any epsilon, which we will define as epsilon 1, or the first epsilon, is greater than 0, there will also be a subsequent delta 1 that is also greater than 0. That is just a, inverse relationship between our, already defined implication. And so we can say that for 0 is less than the absolute value of x minus c, which is less than delta 1, there will be an f of x minus L1 because, we're splitting our function. That is epsilon 1. And then we know this is only possible because based on our delta epsilon definition, this can only work for the limit as x approaches c of f of x equals L1. And this is just essentially what we had. All of this is the formal definition of the limit. And so reason just goes to show that, not the inverse, but the complementary function g of x follows the same rule. We can say that for some arbitrary epsilon 2 that is greater than 0, that necessitates a delta 2 that is also greater than 0, and then there's the same expressions. 0 is less than the absolute value of x minus c, which is less than delta 2, and the absolute value of g of x minus L2, our second limit, is less than epsilon 2. And also, this only works for the limit as x approaches c of g of x equals L2. You know, we're not getting too crazy here. We're just using our limit definitions. And so now, now we're gonna get a little bit crazy. So we're going to do, we're gonna say that both epsilon 1, actually let me look at my notes for a second so I don't get incorrect. We're gonna assume that both epsilon 1 and epsilon 2 are equal to another our arbitrary value epsilon divided by 2, some random epsilon. And then we're just going to plug that into our original expressions, both of them. We'd have 0 is less than absolute value of x minus c, which is less than delta 1. And then this implies, or you could say that if then, because that is the defined relationship, but still, then f of x minus L1 is less than arbitrary value epsilon over 2, and then same relationship, or same expressions, is less than epsilon 2, which implies that g of x minus L2, or the absolute value of that, is less than arbitrary value epsilon over 2. And we're going to say that epsilon, between epsilon 1 and 2, we don't actually know which one's smaller, or which makes this expression more precise. Not that expression, but the whole expression more precise. So we're just going to say plain epsilon is the smaller, okay, this is delta and this is delta. So, yeah, just substitute delta for everything that I just said. We're just going to say that delta is the smaller delta of the two because, you know, delta 1 and delta 2 are both arbitrary values, and we don't know which of these expressions are more precise. So we're going to say that delta is the quote-unquote smaller one of the two. And then if delta, which is, if just delta, not delta 1 or delta 2, if delta is the smaller one of delta 1 and delta 2, that means that since c is the same, c is going to be the same. If delta is the smaller between the two, reason says, I'm going to actually write a full new expression. But just think, maybe pause the video for a little bit and just marinate on this for a second. But if c remains the same, and we have one delta value that is either less than or equal to 1 or less than or equal to 2, then our expressions are 0 is less than the absolute value of x minus c is less than delta. That should be applicable for both our expressions on the right. So, yeah. I mean, I hope that makes sense. Like, let me write the actual expression down. If 0 is less than x minus c, which is less than epsilon, which again is the smaller of the values between epsilon 1 and why do I keep saying epsilon when I mean to say delta? It's getting late, perhaps that's it, but God. We have delta 1 and we have delta 2. That's what I mean to say. I need to go to sleep soon. But we have delta, which is the smaller between delta 1 and delta 2. Delta is not some random value, it is the same value. It's either the same value as delta 1 or delta 2. But since this is either more precise than our first expression delta 1 or our second expression delta 2, that means that this implies both of these expressions in this if-then relationship that we assumed for our formal definition. Okay, so if we add the inequalities together, we can say that if 0 is less than the absolute value of x minus c, which is less than delta, that implies that the absolute value of f of x minus L1 plus, we are adding these inequalities together, plus the absolute value of g of x minus L2 is less than epsilon over 2 plus epsilon over 2. That's relatively basic inequality addition. And since epsilon over 2 plus epsilon over 2 is epsilon over 2 times 2, we can say that this is epsilon. And again, I know this might seem a little abstract because epsilon's not defined to be a number. It's again more of a concept than a number at this point, but still, we're going to say that this is evaluating to epsilon. And so, we're going to get a little bit weird right now. I hope that you guys have at least seen this idea once before, but the triangle inequality for absolute values dictates that the absolute value of a plus b is less than or equal to the absolute values of, not the absolute values, but the sum between the absolute values of a and b individually. That's just a rule that exists. I can't really go into more depth than that. I would have to scrounge the internet for proof of that because I honestly have no clue. But we can say, using that triangle inequality rule, we can say that if 0 is less than or not less than or equal to, less than the absolute value of x minus c, which is less than some arbitrarily small value delta, then I'm going to restate our implication. Then the absolute value of f of x minus L1 plus g of x minus L2 is less than or equal to the absolute value of f of x minus L1 plus the absolute value of g of x, not gx, because that doesn't make sense, but g of x minus L2, which is less than epsilon, because we're just combining this, that idea with, our existing inequality. We're just saying that this is less than or equal to all of that. And so now we're going to, I feel like this is pretty intuitive, but we're just going to rearrange this a little bit and just make it slightly more similar to our base case. Does that work in this context? I don't know. We're just going to say that if 0 is less than x minus c, or the absolute value of x minus c, then, which is less than delta, then the absolute value of f of x plus g of x, in parentheses, just to bring everything together again. Minus L1 plus L2 within parentheses. All of that is less than epsilon. And therefore, that's what we hope to show. That's our original step. And we know now that all of this simplifies to the limit as x approaches c of f of x plus g of x is going to be equal to the limit as x approaches c of f of x plus the limit as x approaches c of g of x. And that's, some people do the little box thing to show that's the proof, but still, this is our original idea. And yeah, I think that was pretty intuitive. And I'm actually going to give you guys a little homework if you want to. But most of these proofs are going to be very similar to that one, because the sum, difference, product, and quotient rules for limits are pretty similar to the sum rule. So I'm gonna write all of them? Yeah, I'm gonna write all of them. So the limit as, I think you already wrote down the sum rule, so I'm not gonna do that one again, but f of x minus g of x, it's gonna be the limit as x approaches c of f of x minus the limit as x approaches c of g of x. And I'm not going to keep saying the same thing over again because that would get very annoying very quickly. So just kind of look at the screen for this one. I don't know why I switched from dots to x's, but okay. And last but certainly not least, the limit as x approaches c of f of x, g of x is equal to the limit as x approaches c of f of x over the limit as x approaches c of g of x. And again, if we use our L1, L2 notation, we can say that's L1 and that's L2. L2 obviously cannot equal 0. Well, I mean, it can equal 0, and we're going to talk about that pretty soon right now. But still, well, okay. So I'm going to actually do, I think you might be able to do this. I think you might be able to do this proof on your own if you wanted to. It mostly follows the same ideas that we used in our sum rule proof, but this one is obviously a little bit more difficult to prove. Should I do a proof for this? Okay, you can comment down below if you want to see a proof for this. But the power rule is also, I would actually go so far as to say that it's most likely one of the most important limit rules that you're going to have to do. But the limit of f of x to the power of some, n, some number n, the limit as x approaches c for that is going to equal L to the power of n, if we're using our, x approaches c, y approaches L notation. And that also seems pretty intuitive, but it is something that you might need to understand a little bit more in depth. But yes, that is a very important limit rule. And, what should I do now? I guess, well, this is kind of common sense. I actually don't think that a proof is even necessary for this one. But the limit as x approaches c of some constant, can't use c because we already used that, but k f of x, that's just going to be k times L if we use our limit notation. That's just saying that you can quote unquote factor out constants in our limits, and that's pretty intuitive. I mean, if you look at any graph and try to find that kind of a limit, like 3x squared, you can factor out the 3 if you wanted to, and you would have the same. Like if we go back to our original example, limit of as x approaches 3 of f of x, then you can factor out the 3, and then, using direct substitution, we can say that 3 squared in that situation would be 9, 3 times 9, 27, and that's obviously going to be the same as if you substituted it in there, you'd have, 3 times 3 squared, which is, again, going to be 27. And I think that's pretty, self-explanatory. But now, I really wanted to get into indeterminate forms, but I feel like that's going to be a much longer video. We're going to talk about, this one is actually going to need some prior knowledge of derivatives. You might self-plug here, you might want to look at my derivatives video if you want, but what we're going to be talking about now is L'Hopital's rule. And since I'm not going to be doing indeterminate forms right now, I think that might be capital. Let's just say that for almost every single limit that is more complicated than limit x approaches 3 of, f of x, where f of x is equal to x squared, for pretty much every limit that you're going to have to do from the point that you learn derivatives on, you're probably going to have to do L'Hopital's rule. And what is it? Well, it is saying that the limit as x approaches c of f of x, well, it's not saying that this is what's happening, but it's saying that if this limit, since we know that this would evaluate to L1 over L2, if we define the limit of this as L1 and then the limit of that as L2. So it's saying that for L1 and L2 in those situations, that if L1 and L2, I wouldn't say evaluates because, again, infinity is not a number, but if it is either 0 over 0 or infinity over infinity, both impossible base cases, we can use the derivative to find the correct or the more accurate limit. And this is a very, very important concept because I don't really like using equals because, again, infinity is a concept, not a number, but still, it'll be for these two cases. But yes, this is L'Hopital's rule. The derivative of some quotient of two functions in which the limit evaluates to either 0 over 0 or infinity over infinity is equal to the... Am I tripping? Wait. It should... Okay. It should be the limit as x approaches c of... completely changes that, but still, it is the limit as x approaches c of that same thing. And this would be if we define L1 and L2. Well, I mean, we don't even have to define that. We know that y equals f of x or g of x, and so L1 and L2 are obviously automatically defined as y values or functions. So L2 prime would be appropriate. So yeah, we're saying that, again, I'll restate it. The limit as x approaches c of some quotient of two functions, f of x and g of x, if that evaluates to 0 over 0 or infinity over infinity, then that limit is also equal to the limit as x approaches c of the quotient of those two functions' derivatives, which is a lot of words. So I'm going to prove it to the best of my ability. And unfortunately, we're going to have to talk about indeterminate forms in another video. You might as well start thinking about it, but it just goes back to the idea that you can't divide by infinity, you can't divide by 0. So 1 over 0, 1 to the power of infinity, on and on. There's a lot of quote-unquote impossible things that happen in math, and to avoid those impossible things that happen in math, we're going to have to do L'Hopital's rule. So we're going to do a proof of that real quick. Even though this is one of the most important rules in both limits, derivatives, calculus, etc., etc., even though this is one of the most important rules that you're going to have to know, this is actually not too difficult of a proof to understand and maybe do a proof similar to yourself. I feel like this is open to many, many interpretations. Well, not many, many interpretations, because eventually we'll have to come to the definition of a derivative, but you can take it in different directions if you so choose. But we're going to say the limit of some function x approaches c of f of x over g of x. And right now, we're going to assume that, oh, crap, I totally forgot about continuity. I feel like we can talk about that pretty quickly, but still. This might actually not make any sense. But yeah, we're going to talk about continuity in like 2 seconds. But we're going to say that f and g are two continuous differentiable functions at a real number c. It's not like 2i or something crazy. We're going to say with all of those assumptions, and if f of c is equal to g of c, which is equal to 0, which makes sense. We're going to try and find this case for like a 0 over 0 or an infinity over infinity. Since 0 is a number, it's going to be a little bit easier to work with than infinity, so we're assuming all of these things. We're saying that these two functions are both differentiable, we're saying that c is a real number, and we're saying that f of c and g of c both evaluate to 0. And with all that red tape drawn, we're gonna actually prove it. So yeah, this one you might even be able to tell just immediately after the first step if you've seen the formal definition of a derivative, which need I remind you at this point is the limit as x approaches c of not x approaches c, sorry, getting too stuck in our limits, h approaches 0 of f of x minus h, or f of x plus h minus f of x all over h. That's the formal definition of a derivative, and so we're going to use that to our advantage right now. And we're gonna actually, we'll see. I might, so in my derivatives video, I talked about how the average rate of change, or, slope, y2 minus y1 over x2 minus x1 is the average rate of change, and how that can kind of like transform into that definition after quite a few steps. So since we're using x approaches c instead of h approaches 0, I'm going to take a step from my previous video. You might want to watch that if this seems like quite a few jumps, but from our y2 minus y1 over x2 minus x1, we can say this would be equivalent to f of b minus f of a as over b minus a, if x2 and x1 were like points a, f of a, and b, f of b. And we're just going to transform that further. If we wanted to make this, perfectly fine function into a more specific function that shows the quote-unquote average rate of change on, I don't know what is happening to my handwriting. It's devolving the closer we get to midnight, but I'm just going to say AROC, the average rate of change, if we want to make that as specific as possible. Even so far as to say the instantaneous rate of change, we would have to try and find some random value at the bottom where we can use a limit. Yeah, so this video kind of leads into that video, and that video leads into this video. But still, if we wanted to make this as precise to one specific point, because, we're operating on like an A to B, and we want to try and find the instantaneous rate of change at some x value c, we would use a limit. We're trying to get as close. So instead of having a and b, we would have like c plus some random value and c minus some random value. It's getting very close to c instead of having a and b all the way over there. So yeah, we'd be using a limit, and the way to write that out would just be the limit as x approaches c of f of x minus f of c over x minus c. And if you want to see how that eventually becomes the formal definition of a derivative, which I think I wrote, it was the limit as h approaches 0 of f of x plus h minus f of x all over h. If you want to see how that goes to that, then you might want to look at my other video. Essentially, just say that x is equivalent to some c plus h, where h is some arbitrary value. But yeah, we're going to use that first definition, which is kind of like a, like a proto-definition of the derivative, and it kind of naturally, very naturally, leads into this. So the limit as x approaches c of f of x over g of x is also equivalent to the limit as x approaches c of f of x minus 0 over g of x minus 0. And we're using 0 over 0 instead of infinity over infinity because, again, infinity is hard to work with. So remember our first assumption that f of c is equal to g of c, which is equal to 0. And we added some minus zeros and minus zeros. It's not some crazy thing that we've done. It's pretty normal. So with this, we can actually say, hey, we know that f of c and g of c are both equal to 0. And we have two newly acquired zeros. So we can say that this function is equal to the limit as x approaches c of f of x minus f of c over g of x minus g of c. And now, this is kind of hard to, I suppose, write a step for. This is more just kind of thinking about it. But if we think about this, let's see. So we know that anything we do to the bottom, or anything that we do to the numerator, we will also do to the denominator. Because we can split both of these into limit, I'm not going to write the full thing out again, but we can say we can split those into L1 and L2. So we know that if we already have this defined relationship between L1 and L2, that anything we do to the top has to be done to the bottom. And therefore, stick with me here, if we divide both the numerator and the denominator by x minus c, we are at the exact same point that we were when we had our proto-derivative. We would have the limit as x approaches c of f of x minus, f of x minus f of c over x minus c, all of that, put parentheses, all of that over, again parentheses, g of x minus g of c over x minus c. That might have seemed like a big jump, but it's just anything we're doing to the bottom. Anything we're doing to the top, we're dividing by x minus c, we're also going to do to the bottom. And using our concept, L1 and L2, we know that this whole limit can be split into two smaller limits, that being, drum roll please, because we're almost done, I promise. That would be the limit as x approaches c of f of x minus f of c all over x minus c, and then all of that over the limit, again as x approaches c, of g of x minus g of c, again all over x minus c. And we defined a proto-derivative. We have this exact thing stored in our memory box, and so we can say that this is a derivative. We can say that this is the derivative at x equals c, or we can say that this is f prime c and g prime c, these two like functions right there. And then this one, this is actually going to make you think a little bit again about direct substitution. We already have f prime c and g prime c, but again, what if c is some value that you can't really do that with? Well, not you can't do that with, but we want to make this case as broad as possible. And so if we try to make that as broad as possible, what we would have to do is unsubstitute. If we imagine that some direct substitution has already occurred, we have c where x should be, we should kind of unsubstitute it in our heads, and we can say that this is the natural evaluation of the limit as x approaches c of f prime x over g prime x. And again, I'm just saying that this is equivalent to that, and essentially we worked one step backwards to achieve our proof. So I'll do that little square thing. But yes, this is the this is L'Hopital's rule. And yeah, I feel like compared to some of the other proofs that we've done, that was a pretty simple one. But yes, L'Hopital's rule is a very, very important rule when you have infinity over infinity or 0 over 0. Not it's not equal to 0 over 0, but if you have these cases, and I will very, very definitely do another video on indeterminate forms, because there are so many different things that are quote-unquote impossible in math until we get it into a less impossible state in which we can make it possible. I know that might sound abstract and weird, but it'll make sense, I promise. And yeah, if you enjoyed this video or you learned something, please comment down below. If you did not enjoy this video and you did not learn something, then constructive criticism is always encouraged. And if you're not in the mood for constructive criticism or a comment, then what exercise haven't I done? Do some bicycle crunches. Okay. And music recommendation. Kind of put me on the spot here. Let me think. What I've been listening to recently. The collaboration of Jim Hall and Bill Evans, I think. I might need to search this up. They have very, I'm sorry, they have very basic names, so it's kind of hard to remember. But Jim Hall and Bill Evans for the stellar album Undercurrent. I don't know who plays who. I think I'm pretty sure. I'm pretty sure that Jim Hall is the guitar player and then Bill Evans is the pianist. But this collaboration is just gorgeous instrumentation throughout. It's just uh, it's just beautiful. Like I really can't describe it any further than that. Just gorgeous instrumentation, um, like perfect composition. It's beautiful. It truly is. Throw it on when you're studying, when you're doing anything. It's not like, I mean, I don't think that jazz in and of itself is abrasive, but I know that like a Thelonious Monk might be irritating to most people's ears. This is very I'm not sure if it's chill jazz. I don't think that this is chill jazz, but this is like it's very listenable. And I feel like it's perfect introduction to jazz for many people who might be put off by some of the weirder compositions. I think Brilliant Corners comes to mind when thinking of chaotic compositions, and this is nothing like that. This is very, not simple, but it's very listenable. It's just gorgeous instrumentation, uh, beautiful compositions, etc., etc. And obviously, these two masters of their arts are just on point throughout. But still, yeah, Undercurrent. If you do choose to listen to that album, comment down below what were your thoughts, and bye.